All right, so if I come into a Google search or any other search, probably if I go SDBS, doesn't have to be capitalized. See, it already shows the database one, but if I just search that, it should get me there. Yep, this is it. It says AIST Spectral Database for Organic Compounds, SDBS. So click on that. And it asks you to agree to these disclaimers. Boom, I agree. I totally agree, 100%. And then I'm here, and you can do some searches here. You can search by the compound name, which I only do that if I'm like 100% certain they're going to name something the same way as me, because a lot of times they'll just have a slightly different naming preference for a molecule, and it won't show up. But if I put the molecular formula, then I can hunt for the name, and I could tell, oh wait, they named it that way. So I usually use molecular formula. And I usually wind up typing molecular formula here and then not realizing I should have put it there. So but here, let me try one. Let's try C8H. Let me guess. No, I'll make it easier. Let's go C4H8O. Let's try that. Okay, so now I'm looking. I've got tetrahydrofuran, common organic solvent. 2-butanone, it ends in -one, it's a ketone. 2,3-butene, 1-all alcohol. So I got a lot of choices here, right? Let's go check them out, see what they say. I'll just start at the top here. So I have the mass spectrum, which we haven't learned about, but we will. And then the carbon NMR we've learned a little bit about, but we'll learn more about it shortly. And then the hydrogen NMR, what we've learned a lot about. And then the IR, infrared spectrums, we're going to learn about those shortly. Raman we're not going to learn about, or the ESR, but we got all this available to us. Awesome. So here, let's go into the Proton Nmr. So here is a Proton Nmr of Tetrahydrofuran. This one is done on a 90 megahertz NMR, a little bit stronger magnetic field than us. Our NMR is a 60 megahertz. And you'll see the structure of it here. And you'll see they got a lot of options for you here. It's got carbons. And there's multiple proton NMRs too, huh? Before we look at those other protons, we can check this out. So what they're saying is tetrahydrofuran, it's a ring, an ether in a ring, and it's got an oxygen right there, and then 4 carbons. These hydrogens are equivalent. They're grouping them together as A, and those ones are equivalent as B. These you'd expect to be a 4-hydrogen triplet, because each one sees 2 neighbors. So 4-hydrogen triplet. So A, they're saying that's at like 3.727 parts per million. That's this guy. Looks kind of like a triplet, huh? A little bit ugly, but that's normal for rings. And then B, it's another 4-hydrogen triplet. Looks a little bit triplety, not that much, huh? But there it is, pretty nice, huh? And then you don't see TMS, because I think maybe I'm not sure how they did it, but I think they might have put TMS in here at a very low concentration. And what they can do is you can zoom the spectrum, like blow it up really high, and then you'd see a little beep for the little bit of TMS, mark it at 0, and then shrink everything back down. That little TMS peak would go so small we can't see it from here. So we are looking at it right now. This is the sample that's in a 90 megahertz NMR, and they use the solvent deuterated chloroform, the most common NMR solvent. That's the one we'll use. And then they have it in other solvents and other conditions too. So here, let's look at this one, the NMR, and this is using deuterated why am I blanking? Acetonitrile? No. Acetonitrile. God, goodness. Yeah, so this is deuterated acetonitrile. Here we go. This one, it was done with a 400 megahertz NMR. So you see how the peaks are a lot tighter? And I bet if we had the ability, I wish we did, but we don't. I bet if we had the ability to like zoom in on the peaks, we'd be able to see that they were triplets. So yeah, unlucky for us. And they have the molecule here again. You know, these 4 hydrogens right next to the oxygen are equivalent. 4 in the back. And then let's check some more. Here's another. This is the most common NMR solvent, I'd say, deuterated chloroform. This is a deuterated DMSO. That's probably the next most common. We have some of that, but it's expensive, so I reserve it for just special circumstances. So this is a 400 megahertz, and yep, it looks similar. It's got 2 signals. These are triplets. You can sort of see they're triplets. I don't know. What do you think? Looks like a triplet, huh? Like a little boom, boom. Boom, boom, yeah. And then we did the deuterated chloroform already. This is deuterated methanol. So there it is, looks the same. That's another 400 megahertz NMR. You can tell the 400 megahertz NMR are their signals are sharper than this one's the 90 megahertz here. Oh wait, that one's not the 90 megahertz. That's 400 megahertz, still sharp, huh? In deuterated chloroform, and they have a 90 megahertz in deuterated chloroform, and that's that one there. Now, yeah, it's a lot rougher looking, huh? Because it's not as strong of a magnetic field. But this NMR might cost you, I don't know, $100,000. Where if you want the high-end one, now you're talking like $500,000 or plus. And then also you have to, this has an electromagnet that the magnet has to be, it's a cryomagnet, it has to be cooled with liquid helium, then liquid nitrogen. And just to constantly having to refill the liquid helium and nitrogen, which evaporates over time, this might be like 50 grand a year just to keep that, just that maintenance cost. So yeah, now back to another one. So that was the first one I just clicked on, right? Return to results. Return to search. I forget which one I want to do. Oh, I didn't want that one back. I did it again. So I did C4H80, I think is what I did, right? Surprised, yeah, remembered it. All right, so if I actually click the one that already came up, nothing happens. This is something that sometimes I sit here and wait. Why isn't anything happening? You could click manually search, but if you just hit enter at this point, now it'll go. All right, we already looked at tetrahydrofuran. Let's look at 2-butanone. We'll go to the Proton Nmr. And here it is. You can see it's this website has for us the mass spectrum, which we'll talk about later. Carbon NMRs, some proton NMRs, some IRs, Raman, which we won't talk about. So right now we're looking at a 90 megahertz NMR sample, and here's our molecule, 2-butanone. So butanone, 4 carbons, right? 1, 2, 3, 4, and this is 2-butanone because 1, 2, the carbonyl is on the second carbon. All right, this carbon right here should be a 3-hydrogen singlet. There it is, look at that, nice 3-hydrogen singlet. And then this one here should be a 2-hydrogen quartet. Boom, there it is, 1, 2, 3, 4, the quartet. And this one should be a 3-hydrogen triplet. It's got the 2 neighbors there. There it is, nice triplet. And then if you're curious of like, oh, well, this one, they all have different couplings, so you can just assign them easily that way because there's a quartet singlet triplet. But if you say you had 2 triplets and you weren't sure which one was which one up here, a lot of times, most of the time, SDBS will have it assigned. So like signal A is at 2.449 parts per million. That's right there. No, right there. That's the quartet for A. And then B is at 2.139. That's the singlet there, huh, for this one. And C is at 1, the most upfield. Oh, and another, I've been using these terms, and you'll just pick them up over time. If a signal that's on the right is upfield of the other ones. A signal on the left is said to be downfield of the other one. So this way is downfield, that way is upfield. Okay, and again, TMS is not showing. That was the 90 megahertz. Let's look at the 400 megahertz probably. Yep, 400 megahertz. And you know, it's interesting. The 400 megahertz spectrum is better. If you have the ability to zoom in, you'd be able to see this a lot better. But on SDBS, the files are low res and you can't really zoom in on them. So it looks, for our experience, it's actually worse in this case, because it's not easy to see that that's a quartet, that's a singlet. The singlet's kind of obvious, but the triplet, that's hard to say, right? But the older, cheaper NMR spectrum is not as tight, all the signals. It's in this view, it's nicer. So, but yeah, so believe it or not, the 400 megahertz sample NMR is way better if you own the instrument, because you zoom in on this and you can see exactly what's going on. All right, so let's look at return to results is what I want to do. We'll take another one. There we go. Let's try this one in alkene. So, boom, HNMR. There we go. Ooh, got stuff all over the place on this one. This is a 90 megahertz, and they're only offering us 90 megahertz. That's all they got on there. They have the carbon and the mass and the IR, but only one of each. That's okay. So here's our molecule. This is an alcohol. It's got the OH there, and it's got a CH and a methyl, a methine, methyl, and then an alkene. And the alkene's got 3 hydrogens, and they're all different. This one's pretty complicated. It's got a hydrogen here that's on a carbon with another hydrogen, but they're not the same because this hydrogen is on the same side as this mess, whereas this hydrogen is on the opposite side. We say this hydrogen is cis to all this, and this guy's trans to all that. So these two are different, and they see, it's a complicated one, but I'll just verbally go through it right now real quick. So it's got 1, 2 bonds away from this neighbor, that's a neighbor. 1, 2, 3 bonds away, that's a neighbor. 1, 2, 3, 4 bonds, is that a neighbor through 4 bonds? It's through a very short double bond, so yes. So this one has 1, 2, 3 different neighbors. So 3 different neighbors, it'll be a quartet. Like, I don't know if it'll be a quartet. These neighbors are not equivalent. So yeah, and it's probably not, and it isn't. So they've assigned it as signal B. So B is the second most downfield, 5.21. 5.21, it's in here, huh? Yeah, so let me make sure. What's C? Is it 5.07? There, it's overlapping actually. It looks like B and C are kind of overlapping. 5.21, 5.07. Maybe not. B is there, probably. And yeah, I think this is, let me zoom in a little bit. This is part of one of the hydrogens. This is part of the other one, and then they overlap a bit here. So it's a mess, and it doesn't look like a quartet at all, right? As expected. And then the most downfield of the alkene ones, A here, how many hydrogens does it see? It sees that neighbor 3 bonds away, 3 bonds away, that's 2. And it also 1, 2, 3 bonds away to that, sees that one. Does it see these? Let's check. 1, 2, 3, 4. But it went through all single bond, or a CH, we always have that. Carbon-carbon single, carbon-carbon single, too long. So I'm going to say it has just 3 neighbors. They're all different. So quartet, does that wind up looking like a quartet? No, it's a mess, huh? That's the question mark, what I mean when I'm like, I don't know if it's going to be a quartet, and it's not. So there we go, we got those 3. And then next up, this guy, all by himself. How many neighbors does he see? So he sees 1, 2, 3. He sees these 3 and these 3. Oh no, just these 3, huh? We're going to assume oxygen cuts off the coupling. Yeah. So all he sees is those 3 neighbors, and this guy. That makes 4, and then 1, 2, 3, 4. Yeah, he sees that guy and that guy. Wait, there's a lot. He sees these 3 and these 3. So he sees 7 total. So he's looking like a octet. No, did I say 7 total? No, he sees 6 total. He sees these 3. 1, 2, 3, 4. Yeah. 1, 2, 3, 6. He sees 6 total. So he's a septet. And they are calling him D, this guy. And so, yeah, I don't know, that looks like a septet. 1, 2, 3, 4, 5. Yeah, I think it's a mess. If we had the ability to zoom in and see this better, we'd see it's probably not really a nice septet. So that one's, yep. And then this end one, though, this last one here is really nice because it's it only sees that neighbor. So it should be a nice doublet. That's the F one they're talking about right here. Nice doublet, huh? 3 hydrogens. And notice how this 3 hydrogen signal is taller than all these 1 hydrogen, 1 hydrogen, 1, 1, 1. So that's good. And then the alcohol by itself, it's not coupling through the oxygen as we normally see. Sometimes you do get coupling through oxygen, usually not. And when it doesn't couple through oxygen, then you're a singlet, and that's what they're saying. E is right there too, so it looks like a singlet. Alcohols or hydrogens in general that can hydrogen bond, so hydrogens usually on oxygen or nitrogen, they a lot of times are broad like that too. That's another sign there. And they got the peaks listed. And then this is the coupling constant they're telling us about, D to F. Yeah, they're just giving us that one. So what that is telling you the distance in hertz between this doublet signal here. D to F, D, and then G, yeah, and then it's in there too, but it's complicated with the other ones. So yeah, that's we'll talk more about coupling constants later. And the distance that a peak is split, we measure it not in parts per million, but in hertz. And you know, parts per million is derived from hertz, but we'll talk about why we use hertz to measure it. It's a nice small number too, like 6.5, 8, 18, something like that. All right, so that was pretty good. I could return to results and continue on, but I'll let you guys jump in. Oh, and I was hoping this would happen. If you're at a a particular spectrum like we just were for a little while, like it's pretty short amount of time, like a couple minutes, it kicks you back out to this disclaimer. They really want you to read this. And yeah, I haven't, but I just agree again. And then it's kind of annoying. Sometimes you have to, re-input your value, but not that big a deal. And hey, beggars can't be choosers. This is all free. C4H8O. So boom, hit enter, and I'm back in it. There we go. I could, if I wanted to get back to another, that was one I was at, the butanol. Oh, I have a story. So this website, it's a Japanese website, and when the tsunami hit Japan a few years back, and they had the nuclear power plants leaking radiation, and the whole country was shut down for a little bit. It was super sad and a horrible event. And during that time, this website was closed down. And I noticed how often I used it. I would keep coming to check it throughout the day at school, and I'd be like, oh wait, it's closed. And my first instinct would be like, oh shoot, that website's down. I'm like, oh, my free website's down. Not poor me. These people are getting like hit with radiation. I'm worried about my website. But the Japanese country is strong. Within like less than a week, it was back online and going for it. All right, now it's your turn. Now you guys can do a search like, I gotta go back this way, huh? You can do a search like, I said to do C5H something, I think. I don't know if I said E5. I probably did C5H10O. But make up whatever you want. See what you get. Oh, we got a lot of different stuff here. Cyclopentanol. Boom. Proton Nmr. There we go. Look at it and spend a little time. Like maybe I think it's best if you took a piece of paper and pencil, drew this out, bond line form, and try to circle the groups, predict coupling, and then find their peaks. If you do that a few times, just spend 10 minutes on it, you become much better at this stuff. All right, thanks.